Here we're writing the reaction products for a series of reactions from chapter 20 of the Klein text. And included in these reactions are going to be a couple that you may have seen in previous labs or you will be seeing in labs in the short future, labs such as it is at the moment. So in this first one, we have a compound that contains a ketone carbonyl and a carboxylic acid carbonyl. And it turns out that this particular reagent, BH3THF, specifically reacts with carboxylic acids and not with ketones. So the ketone is preserved and we get a primary alcohol at the site of the former carboxylic acid. And I'm not sure that they talk about that in the UCI lectures, but it's definitely in the Klein text. It's in the carboxylic acid section at the beginning of the chapter. So this next one, we have a carboxylic acid that reacts first with thionyl chloride. So that's going to make the acyl chloride. And then, because acyl chlorides are so reactive, and these cuprate reagents, also known as Gilman reagents, aren't as reactive as Grignard reagents. Copper isn't as electropositive as magnesium, so they're less reactive than Grignards. So that combination means that the cuprate will react with the acid chloride, but it won't react with the ketone that's the first form product. So here what we're going to get is the compound where we've added an ethyl group to the carbonyl, and it stops here because the ketone is not reactive enough to react with the cuprate. And this is different than what we saw with a Grignard, where the ketone would definitely react with the Grignard. So this is a handy way of stopping at the ketone. And there are a couple reactions like this in this chapter that exploit different reactivities, either in this case for an organometallic to stop at the ketone, and then there are also some where you take carboxylic acid derivatives and you're able to stop at the aldehyde instead of going all the way to the primary alcohol. So this next one is the first of the reactions that I mentioned that pertain to lab, and this is a lab experiment that we will be quote-unquote doing in Chem 24 fairly shortly, for those of you who are in Chem 24. And so we've got an acyl halide, benzoyl chloride, and an amino acid. This happens to be glycine. And instead of using an excess of the amino acid or adding pyridine, what we do when we do this particular lab is we add sodium hydroxide dropwise and monitor the pH. And the idea is to keep the pH high enough so that we have this form of the amino acid. As you raise the pH, what's going to happen is you're going to protonate this nitrogen before you protonate this oxygen, and then you don't have a nucleophile anymore. So what's going to happen here is we're going to get an amide, and the form that we're going to have at low pH is going to be the anion, but I'll go ahead and write the form after acidification, and this is benzoyl glycine, and the general name would be a benzoyl amino acid. And then some of the fun things that we do with this is an NMR study. But you'll have to wait until Chem 24 to learn about that. So this next reaction is a reaction that, believe it or not, we used to do in Chem 11, back in the day when we did a little bit more organic chemistry in Chem 11. And you take acetic acid, salicylic acid that you might remember from Chem 21 if you took it at SMC. And although, you might look at this and you think, well, I've got two OHs here that could potentially react with the anhydride. What's going to happen is this one is more reactive, it's more nucleophilic, and so therefore that's the one that's going to react. And so the product that we're going to get here is known formally as acetyl salicylic acid. The byproduct that you would get would be acetic acid. And acetyl salicylic acid is better known as aspirin. So here we have a whole bunch of steps. And this is one of the reactions I mentioned earlier that we're able to stop at an aldehyde ultimately. So looking at the first couple steps, we make a Grignard, we carbonate the Grignard, and we protonate it with acid. So let's write what we get after step 3. So after step 3, we have this carboxylic acid. And so notice that what we've done is we've made a carboxylic acid and we've also added 1 carbon. You can compare that to adding an epoxide where you add 2 carbons and get an alcohol. The reason why we protonate with H3O plus here instead of water, as we've done with most of the proton transfer steps after adding a Grignard, is because the carboxylic acid is acidic, and in order to protonate it, you need an acid. If you just added water, you'd end up with the anion of this compound. So now we're going to keep going here. And the next thing that's going to happen, we're going to react this with thionyl chloride. And that will make the acid chloride. And then acid chlorides are super reactive. Again, we're going to exploit that. And they'll react with this particular reducing agent, which you can see is kind of modeled on lithium aluminum hydride. So instead of 4 hydrogens, it has 1 hydrogen and 3 alkoxy groups, and the R group here is tert-butyl, which I noted over here, although I should have an asterisk. And again, what that does is it reduces specifically acid chlorides, and anhydrides, to an aldehyde, and it stops here because the aldehyde is less reactive than the acid chloride. When we reduce something like an ester or carboxylic acid, the aldehyde that we get from that initially is more reactive than the starting ester or carboxylic acid, so we don't have that outcome. But this reducing agent is not active enough, it's too sterically hindered to react with anything but the very reactive acid chlorides and anhydrides. By the way, in the UCI lectures, she kind of disses this reagent and another one of the specific hydride reagents, and apparently based on life experience says that you're actually better off reducing all the way to the primary alcohol and oxidizing back up with PCC, but I have no experience with it, so I'll leave that there. So here's another reaction that we'll be doing eventually in Chem 24. Mercifully, this is one of the ones we videoed ourselves, so we don't have to make half the lab up. And so we've got a carboxylic acid and an alcohol. Carboxylic acids aren't particularly reactive, so we need the acid catalyst to protonate the carbonyl oxygen. And this is known as a Fischer Esterification. And obviously we're going to make an ester out of this, and the ester that we're going to make, I'll make a longer arrow. And we have 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4, 5. There we go. Okay. And so this is known as isopentyl acetate. If you go back a bit in history, it's another name for the pentyl group is amyl, so it's isoamyl acetate. And the esters are said to have pleasant fruity odors, and this particular one smells like kind of a synthetic version of bananas, and therefore the compound is referred to as banana oil, extremely casually. So when we do this lab in Chem 24, we don't actually use this particular alcohol. Instead, we use a variety of unknown alcohols that have either 5 or 6 carbon atoms. And so those of you in Chem 24 will get to experience that. So number 7 is a tripeptide. I'm tired of red. Is a tripeptide. And so when you have peptides, they're linked together via these amide bonds. So you look for the bond after the carbonyl. So we have an amide bond here and an amide bond there, and those are what's going to hydrolyze under these reasonably extreme conditions of strong acid and heat. The 3 amino acids that comprise this particular tripeptide are glycine, that we met in one of the questions above, alanine, and valine. And so when we name the tripeptide, we can use the 3-letter abbreviations for the component amino acids, and we call it gly, ala, val. And the convention when writing peptides is that the N-terminus, or the free amine, is on the left side, and the C-terminus, or carboxylic acid, is on the right side. And that's just a convention in biochemistry. And what I've written here in terms of the peptide, tripeptide, is I've written this in its completely protonated form. So the carboxylic acid is protonated, and the amine on the end is protonated, because that's what's going to happen in strong acid. So it's a tripeptide, so we're going to get 3 different amino acids out of this. And kind of in order, we've got H3N, and I'm going to write them as they would be formed if this thing cooperates. I'm going to write them as they would be formed in acid. So we have this compound, which is glycine. And then we have H3N. Should get a positive charge. And then it goes like that. And this is alanine. And then the third one that we're going to get is this one, the valine, where you have the side chain is an isopropyl group, whereas in alanine the side chain is a methyl group, and in glycine the side chain is, well, hydrogen. And we'll see how much biochemistry we end up doing this semester, so that might be, your tripeptide biochemistry for the semester. And again, as I've mentioned before, amides are not particularly reactive, so you have to work pretty hard to hydrolyze these bonds. It's an experiment we used to do in what's now Chem 31, sort of. And we would actually seal these things in vials and heat them in the oven for days in order to get them to do the hydrolysis. So this next reaction should look familiar, hopefully, to those of you who took Chem 21. So what we have here is that wonderful to pronounce thing, methyl salicylate. You might remember the smell. It's also called oil of wintergreen. And what's going to happen here is we have an ester, and we hydrolyze off the ester. And this is an example of the base-promoted hydrolysis of an ester, which is also known as saponification. And so what will happen here is initially in base, the first thing that happens is we remove the phenol hydrogen, but then once the reaction occurs, we have the anion of the carboxylic acid, the anion of the phenol, and this was soluble in the basic solution that you got initially, and then when you add the H+, you protonate both of the anions, and you make salicylic acid. Notice a couple things. First of all, with the naming, salicylic acid, even with kind of a common name, the ester nomenclature still follows. We have methyl, drop the ic acid, and replace it with 8. One of the reasons we do this experiment in Chem 21 is that it introduces some useful techniques like reflux and recrystallization, and we also identify the product by carbon NMR, but it's also kind of satisfying because if you do it well, especially the recrystallized product is these really pretty needles that you may or may not remember. So there's the lab that we did in Chem 21. All right, so this next one, first we're going to take MCPBA, and the MCPBA is going to make an ester, so we're going to insert the oxygen here next to the tertiary carbon, but it's not that size ring. All right, so when you draw a 7-membered ring, you want to kind of start like you would a 6-membered ring, and then you can bring the next 2 sides out and then finish it off so you kind of have a pumpkin. And there's your 7-membered ring, or I guess another option is you can purchase a template. And these cyclic esters are also known as lactones, and eventually we'll learn how to name them, like soon after the amine chapter. So now we're going to take our cyclic ester and we're going to hydrolyze it. And when you hydrolyze an ester, you get a carboxylic acid and an alcohol. And that's exactly what we're going to get here. It's just that they're going to be attached to each other. So we have our carboxylic acid, and then we have 1, 2, 3, 4 methylenes. So 1, 2, 3, 4 methylenes. And then we have a carbon which is attached to 2 methyl groups and an OH. And it's fine if you draw things this way. You can beautify it if you want, but I'm not going to bother beautifying this at the moment. I'm just going to leave it unbeautified. So here we have a reaction that also harks back a little bit to a previous chapter to electrophilic aromatic substitution, and I'll go through why it harks back to that. So the first thing that we're going to do is chapter 20 chemistry. So we have an amine and we react it with acyl chloride, and we could either use an excess of this amine or we could use pyridine, and I put pyridine in, and pyridine is just serving as the base that will sop up the acid that's produced in the reaction. So the first thing that's going to happen is we're going to make this amide. And now we're going to do a Friedel-Crafts reaction on that amide. I'm going to get rid of that highlight because it's kind of dark, but we're going to do a Friedel-Crafts. And what we have here is an ortho-para director, so we'll get mostly para product. And we're going to put an isopropyl group on. And then in these last two steps, we hydrolyze the amide back to an amine and a carboxylic acid, and then deprotonate the amine. And so what we're going to end up with when we do that main product is the amine, and then we'll also get some acetic acid. I imagine you have to be somewhat careful with that protonation step so that you can, well, it's probably pretty easy to separate those two compounds. So some of you might be wondering, why did we do this? So why couldn't we just take this compound and react it in the Friedel-Crafts and be done with it? Wouldn't that be simpler instead of doing extra steps and violating some sort of scientific principle? Maybe it's Occam's razor. It's not really an explanation though. So the purpose of this is that this group is very highly activating, which is fine, but it's also a base. And if we take this base and the aluminum chloride, which I see now is written as AlC3, I can fix that. It forms a complex. So you would have, let's pick a better color here. So if you have those two compounds, you would have your aniline plus your aluminum chloride. And what happens is those two things form this complex. And notice that what you've done is you've now converted a highly activating group into a metadirector. And if you have a metadirector, you're not going to get any Friedel-Crafts alkylation or acylation. So the purpose of these extra steps is to sort of, I guess you could call it a protection of the amine group. It's sort of a deactivation of it in a way, so that it doesn't react in a way that we don't want it to react. Now I need to move this down because I ran out of room for it. So this is something I think they talk about in maybe in the electrophilic aromatic substitution chapter, but you kind of don't understand what's going on, and I thought it would be helpful to do an example so that you could see what's going on. All right, and finally, we have benzyl bromide, another one of those innocent substances that's kind of nasty. It's a really bad lacrimator. It makes you cry like onions, but worse. So what we can do here is this first step here is just an SN2, and that's probably the most useful way to make a nitrile. By the way, students sometimes get confused with the various ways of writing this. So those two things are equivalent. I got a question about that during the test last night, so there you go, nitrile. And then when we reduce the nitrile, what happens is, it's good I drew that. What happens is you add two hydrogens across that carbon-nitrogen triple bond. And so what you're going to get is we've got 2 carbons, is a primary amine. So this bond is this bond is this bond, and we should have 2 carbons in addition to the nitrogen. So what the cyano group does overall is it adds 1 carbon, and I happen to do a reduction here. You could also take this nitrile and you could hydrolyze it to carboxylic acid, although it might be easier just to make a Grignard reagent out of this and add CO2. Another thing sort of to keep in the back of your mind is that this is the same amine that we would have gotten from the corresponding amide to this. And since the nitrile has a triple bond, we can only make primary amine